Welcome everybody to this first session on mixed models. This workshop builds on a number of things that we've covered previously. So we're going to take our first look at generalized linear mixed models. We're going to look at how we build models with a combination of different fixed and random effects. I'll explain that in a lot more detail in a little bit, but it's basically the idea that we can model individual participant variation, and we can also model individual item variation simultaneously alongside the experimental conditions that we're interested in examining. We're going to focus on designs where we have one experimental factor with several levels. We're also going to look at 2x2 designs, so basic factorial designs, where we have continuous data on our dependent variables, such as reaction times, for example. We're also going to then look at how we determine model fit, and in terms of interpreting interaction effects, much in the same way that we did with analysis of variance, we're going to be using the em_means function from the em_means package to conduct pairwise comparisons. So I guess the basic question we might ask ourselves initially is, well, why do we want to build linear mixed models in the first place? So it's worth noting that linear mixed models are very flexible. They're much more flexible than analysis of variance. They allow us to model multiple random effects simultaneously, so we can kind of model individual differences within our participants, within our experimental trials. We can also model simultaneously subject and item covariates. We can build these models for unbalanced designs where we've got different numbers of participants in our different experimental groups. Linear mixed models cope nicely with missing data points. They allow us to model both continuous and categorical independent variables, but also dependent variables too. They operate over trial level data, so in contrast to analysis of variance, which operates over averages for our experimental conditions by subjects, for example, mixed models operate over trial level data, so they're using a lot more information that's in our data set to build the model. And for all of these kind of reasons, they actually provide a really nice balance between type 1 and type 2 error. And they allow us to build different kinds of models to fit our data and allow us to determine which models make most theoretical sense. And in many areas of psychology now, people have moved away from analysis of variance approaches to analysing data and have adopted mixed models approaches. Certainly within areas such as language processing, it's very rare to find a journal article in a decent journal these days which doesn't use mixed models to some degree. So mixed models are actually relatively straightforward in the sense that conceptually they build on stuff we already know about. So we're just going to have a little bit of a quick revision at this point, and we're going to look back at what we learned in the context of linear modelling, which is where we're trying to predict some outcome variable if we know some predictor. So here's a very sort of basic example where we have 8 participants. We measure their gender and we measure their height. And our basic question might be, can we use information about somebody's gender roughly to predict their height? In other words, is there a relationship between these two variables? So we can plot the data. I've just added a little bit of jitter to make it easier to see. So we've got our female group here, people who identify as female, and we've got our male group over here, people who identify as male. So it certainly looks that on average, males are taller than females. So let's fit a linear model using the LM function. So this is exactly the same function to build a linear model that we used in the context of the regression workshops. So we're going to create a new variable called height underscore model. And we're going to say that height underscore model is the linear model such that height is predicted by gender, and we're using the data set gender height data to do that. So if we build our model and then ask for a summary of the model, we're going to look at our parameter estimates. So we see that the intercept is 165. So that corresponds to the average height of females. This is our reference category. If you remember, R uses dummy coding, unless you override that, which basically means that it's going to take the alphabetically earlier level of our factor as the intercept. So F comes before M, so 165 corresponds to the average height of our females. We've got a parameter estimate for our gender male level, which is 12.5. What this means is that males are, on average, 12.5 centimeters taller than females. And we've got a t-test on our gender male level. It's significant. It's 0.017. So we can kind of see that on the basis of the model, that we can fit a linear model such that it predicts the average height of our females and the average height of our males on the basis of gender information. And we can just sort of do the plot like that. So that's when we have a categorical predictor, i.e. gender, predicting our continuous outcome variable. But what happens if we have a non-categorical predictor? In other words, we want to predict using a continuous predictor. So here's a similar case where, again, we're wanting to predict height, but this time we're looking to see whether or not we can predict height on the basis of knowing somebody's age in years. So we can look at our data set over here. We've got 8 participants. We've got their ages in years measured. We've got their height measured in centimeters. So a quick plot that we've done over here suggests that there does indeed appear to be a linear relationship between these two variables. As people get older, they certainly seem to be taller. This is certainly a relationship that we can see in this very limited data set, but it seems to be one that we could potentially model. So we're going to build a linear model, much as we did previously, but rather than having gender, a categorical predictor, we're going to have age, a continuous predictor to predict height. So we go about building the model in the same sort of way. So we use the LM function where we have height is predicted by age, and we're going to use the data set age height data. So if we were to build that model and then ask for the summary, we get information about the intercept and information about our predictor. So we interpret this as meaning that for every increase in age by 1, height will increase by 2.398 centimeters. And that's a significant predictor. We've got a t-value and an associated p-value. So we kind of know for our data set, certainly, that there appears to be a linear relationship between age and height. But of course, we kind of know that over the broader lifespan, this relationship likely breaks down. But certainly for the data set that we have, we can fit a linear model to our data. Okay, so that's kind of a summary of linear models in general, both with a categorical and with a continuous predictor. So linear mixed models are kind of taking this an extra stage. And in the context of building mixed models in R, we need to use typically 3 separate packages. We're going to use the LME4 package. The LME4 package is the package for building mixed models of all different sorts. We also need to use the LMER test package. What this will do is give us p-value estimates for our model parameters. It uses a method to estimate the degrees of freedom. So we've got p-values then in our model output. And the EM-means package is the same package that we used previously in the context of analysis of variance, which helps us run pairwise comparisons with various corrections for multiple tests. So let's think about linear mixed models for a second. So what happens when we've got many observations per person that we want to model? So imagine we carried out a study where we're interested in how a person's reaction time varies as to whether they're responding to visually large or visually small target items that appear on the computer screen. So further imagine we've got 10 people, each responding to 5 large and 5 small target items. So what this means is that for each participant, we have 10 observations per participant. But of course, within a participant, each of these observations is not independent of each other. And one of the assumptions of the linear model, so one of the assumptions of analysis of variance, say, is that the observations in our model are actually independent of each other. But that's not the case here, because you can imagine one individual, for example, might just have a pretty fast set of reaction times in general. Another individual might have slow reaction times in general. So all of the observations for the kind of fast reaction time person will tend to be pretty fast. So there's kind of something of the individual differences of our participants that's kind of captured by the fact that responses within a participant will actually be quite similar to each other. In other words, they won't be independent of each other. What's nice about mixed models is we can actually get around this lack of independence by treating participants as what's known as a random effect. What that effectively lets us do is model each participant such that they have their own individual reaction time baseline. So we can actually capture that those individual differences in our mixed model. So we can do that by modeling participant as a random effect. So this will give us a separate random intercept for each participant. So it's going to give us a measure of their kind of baseline reaction time speed. So if we look at the model specification down here, it doesn't look too different actually from what we were looking at earlier in the context of linear models. We've got reaction time is predicted by condition plus, and this is the important bit, this is our random effect term and models each subject as having a different random intercept. In other words, a different baseline, a different reaction time baseline. So that's what that notation here means. And then there's some sort of error term, or error that we're just not able to model. So this is our mixed effects model. We've got a fixed effect and a random effect. But let's take it a stage further. So we talked about the fact some participants might just be faster than others. So different participants will have different reaction time baselines. In addition to having multiple participants in our experiment, we've also got multiple target items. So imagine we have different target items presented to our participants. And not all of these target items are going to be equivalent. So it could be the case that some target items people respond to more quickly than other target items. In other words, you can kind of think of the fact that target items themselves will have individual baselines too. And we want to be able to capture that in much the same way that we capture the individual differences between our participants. And we do it exactly the same way. We introduce a random effects term which allows us to model the individual differences between our target items. So here's the model we had earlier, but now with an extra random effects term corresponding to the fact that we're modeling our items as having different individual reaction time baselines. So we've now got a mixed effects model where we've got a fixed effect of condition, so that's our experimental manipulation, a random effect of participants or subjects, and a random effect of items. So this combination of fixed and random effects basically defines what a mixed model is. So fixed effects are typically experimental conditions in the context of the sort of experiments we might be running, where we have data that has been gathered from all of the levels of the factor that might be of interest. And you might have an experimental factor, such as, older people versus younger people, and you've got data from both of those levels. So important then to think that when you have a fixed effect, you've actually got data at all levels of interest. A random effect is slightly different because the factor could have many possible levels, and we're interested in all those possible levels, but we've only got a random sample of all levels included in the data. So you can think of, all the participants in the world. Each participant would be like a different level of a random factor, but we can't collect data from all participants in the world. We're collecting data from a sample. So we kind of recognize then the fact that our participants are just a random sample, therefore a random effect. And typically in research, we'll model participants as a random effect, probably items too. And typically we need to have at least 5 levels in order to estimate the kind of parameters of the effect appropriately. So you need a decent number of participants, a decent number of items in order to be able to model the random effect of these two sources. So let's look at a specific example then. So this is the case where we had participants looking at images that were visually large or visually small, and we measured their reaction time. So we've got 400 different observations, and we've got 4 columns in our data. We've got subject, item, condition, and reaction time. So we've got our participants listed, items listed, condition listed, and a reaction time listed. So the first thing we'll want to do is just generate some summary statistics. So we're just going to do that as we've done previously. We're going to take our data set, which is mixed model data, and then we're going to group it by condition, and then we're going to generate some summary statistics such that we've got mean underscore RT, which is going to be the mean or average reaction time, and SD underscore RT, which is going to be the standard deviation. So if we look at the descriptives that are generated, we see that people actually seem to be a little slower responding to the large items than to the small items, okay, for whatever reason. But that's kind of what the descriptives suggest. And the standard deviations are roughly the same. So let's build our mixed model. So the model specification is up here. Rather than use the LM function, we're using LMER. Otherwise, it's fairly similar. So LMER, RT, so reaction time, is predicted by our fixed effective condition plus a random effect of subjects plus a random effect of items. And we're using the data set, mixed model data. And then we can ask for a summary. So we get lots of information in the summary. Not all of it is equally relevant to us. What we're going to focus on first of all is this set of random effects. So we can look, we've got the random effects of subject, random effects of item, and we can see we've actually got a lot more variability in our subjects than in our items. And that is probably fairly typical. But the important thing in terms of determining whether or not our experimental manipulation has had an effect is down here. So we see that we've got an intercept of 854. So that's the average reaction time for responses to the large visual images. So L comes before S. So the intercept corresponds to the reference category of large visual images. And then small images are responded to 49.78 milliseconds quicker than large ones. And that's significant. The t-value is 5.897. The p-value is minuscule, so the scientific notation here simply means move the decimal place 9 points to the left. Okay? So we see that the intercept corresponds to the reaction time to the large condition, fits our descriptive statistics. Okay? And going from large to small decreases reaction time by around 50 milliseconds. So we can see that the experimental condition is significant. We've got a tiny p-value. Now, another thing that we could do, if we wanted to, is compare this model that we've built to model our data with another model where we actually drop our experimental manipulations. We drop our fixed effect, and we look to see which of these two models is better in terms of capturing our data. With the idea being that if the model with the fixed effect is better than the model without the fixed effect, then the fixed effect itself is obviously contributing variability in our data set that we can model with the mixed model that includes that fixed effect. And we can do it much more effectively than building a model which doesn't have that fixed effect. So what I'm going to build now is what I'm going to call a null model, which is identical to the model that we built earlier, apart from the fact we don't have a fixed effect. We're saying that our reaction time is predicted by our two random effects in this case, and nothing more. So we can actually compare these two models to each other using what's known as a likelihood ratio test. So we can actually look to see whether or not the model with a fixed effect is better as a way of capturing our data than the model without the fixed effect. So we can use the ANOVA function with our two models that we've built, and that will conduct a likelihood ratio test comparing the two models to each other. We get a number of bits of information about our two models. AIC, which stands for Kiki Information Criteria. BIC, which stands for Bayesian Information Criteria. Basically, for both of these, lower numbers are better. They capture the amount of information that's not explained by our model. So if we were to focus simply on AIC at this point, we can see the AIC value for our model that only has random effects is 4751. The AIC value for our model, which has got an additional fixed effect, is 4720. So on an AIC basis, the model with the fixed effect is better than the model with just the random effects. So fixed effects plus random effects is better than just random effects. And it's the same case on the BIC measure. Deviance here for linear models corresponds to residual sums of squares. Okay, so there's less, deviance is less for our model with the fixed effects plus random effects than it is just for our random effects model. And we can see here that the two models compared to each other, they differ significantly from each other. So this is a nice case where all measures of kind of model fit tell us that our mixed model with a combination of fixed effect and random effects is actually a better way of capturing our data than the model with just the random effects. So this tells us quite clearly that this fixed effect corresponding to our experimental factor is explaining a significant portion of the variability in our data set. I just want to note one thing at this point in the context of comparing an experimental model which contains a fixed effect as well as the random effects with a null model that contains only random effects. You can only use the likelihood ratio test if one of these models is nested in or a subset of the other. Okay, so it's quite a useful test to use, but make sure you use it appropriately. The models have to be nested within each other. In other words, one model has to be a subset of the other. So far, we've been talking about modeling differences in terms of the baseline, different baselines between participants, different baselines between our items. But of course, you might imagine for some participants that the actual magnitude of the difference between the experimental conditions differs from one participant to another. So for one participant, the difference between the two experimental conditions might be really huge for whatever reason. But for another participant, they might still show the pattern of effect, but the actual magnitude between the two experimental conditions might actually be much less. So what we want to be able to do in addition to modelling the different baselines for our participants and items is we also want to be able to model the differences in the magnitude of our effect, both for our subjects and for our items. So that's what we're going to sort of look at now in the context of mixed models. So how do we actually do that? So far we've been assuming a constant magnitude of the effect across subjects and items. And we can actually look at that by asking for the coefficients of our mixed models to be generated. And we actually see we've got separate coefficients for each of our different participants and each of our different items. So we've got a different intercept. So that's basically a different baseline for each of our different participants. But the difference between our large condition and our small condition, well, actually, with the model we built so far, it's the same across participants and across items. So far, we haven't taken account of the fact that the magnitude of our effect might be bigger for some subjects than for others, and for some items than for others. So we need now to be able to model the fact that the magnitude of the difference between our large and small condition might actually vary as a function of participant and as a function of item. So in order to do that, we add what's known as random slopes to our random effects terms. And we simply add our fixed effect here as a random slope for subjects and as a random slope for our items. And what these modified random effects terms tell the model to do is expect different intercepts for our fixed effect, which is what we had previously, but also expect the slope, in other words, the difference between our experimental conditions to differ for subjects and for items as a function of our experimental manipulation. So we're not just modelling now baseline differences between our subjects and between our items, we're also modelling differences in the order of magnitude of the difference between our different experimental conditions. So if we do that and then look at the coefficients for that model, we now see that in addition to different baseline estimates for each of our different participants, we've now also got different estimates corresponding to the magnitude of the effect size, or of the difference between the levels of our experimental factor. So you can see for participant 1, there's just an 11 millisecond difference between the response times to the large condition and the small condition. But for participants 8, 9 and 10, they've got sort of 69, 70 millisecond differences between the large and the small conditions. And if we look at the items as well, we can see that the items range from from 28 milliseconds for item 3, difference between the two versions of the item, and 72 milliseconds for item 4. So we're modelling now a lot more information that's provided by our data set to gain a better understanding of what influence our experimental manipulation has had on our reaction time measure. And we can actually plot these different coefficients if we want to. So we can see over here, we've got our participants plotted, and we can kind of see they're all basically showing the effect, but the kind of slopiness of the line suggests that the effect is greater for some participants than it is for others. So subject 1, this line here, is showing a pretty small difference between the two experimental conditions, in contrast to, say, subject 3, who's showing a much bigger difference between the two experimental conditions. We kind of see them highlighted down here. So for subjects, we've now modelled the fact that the magnitude of the difference between conditions varies from one subject to the next. And we've also done the same for items. So again, we can see over here on the left, all items are showing the effect, but for some items, the effect is, the magnitude of the effect is greater than for other items. And we can kind of look at items 1 and 3 here. So under the small condition, for the small condition, items 1 and 3 are roughly the same. But for the large condition, item 1 is about 25 milliseconds slower than item 3. So we can kind of see there's variability in our experimental items that we've now been able to model as well. So I'm not going to go into details of what's going on under the hood in the context of linear mixed models. They use something known as partial pooling as a way to estimate the parameters of the model coefficients. And very generally, partial pooling takes account of the individual slopes and intercepts for each level of the random effect structure, but also the slope and intercept of the overall model. So you can kind of think of it as basically building a regression model of the overall data set, but also separate regression models of the individual participants and the individual items, and almost finding like the best fit between these sets of models. But the use of partial pooling is one reason why mixed models are so powerful. They can cope with missing data because they can be sensitive to properties of the overall data set. They're not too affected by extreme data points because in the context of the data set, generally, in a sense, the model kind of knows that these extreme data points are quite unlikely, and their influence is actually reduced in the context of mixed models when those models are built. And this is a property known as shrinkage, which kind of reduces the influence of these kind of extreme values on the parameter estimates. But if you are interested in reading more about what's going on in the context of mixed models, in the context of pooling and partial pooling, I absolutely recommend this blog post linked at the bottom of this slide by Tristan Marr, where he goes into a good amount of detail, both lots of nice examples as to what is actually going on with mixed models in the context of how they use these different pooling methods to arrive at an overall solution. So that's kind of a general introduction then to linear mixed models.